So here's the construction of pi. You start off with what you want. All right? And then what you do is you say, well, if that's the case, then pi times p minus s cross nu plus s cross nu is equal to pi. All right? And then let's stare at this for a bit. Okay, remember, row vector matrix. Row vector matrix. This is just matrix vector multiplication. It really is. It's just that. I mean, again, pi of I equals the summation over j of pi of j pj to I. Right? Pi p equals pi means that. That's pi times p. That's a row vector times a matrix. Can you imagine how weird I feel having to say that? But I know that half of you don't know what I'm talking about. But you all agree that when I multiply row vector times a matrix, I'm just doing that. I know you're laughing, but I know from experience that more than half of you have no idea what I'm talking about. And it's just, you're lost in the notation. Don't be. I'm just talking about matrix multiplication. All right? And the same thing here. As soon as you see the cross here, you're thinking, whoa, I'm going to sleep now. But I just don't want, if I write S nu, it'll look weird. I want to emphasize that this is a column vector, and that's a row vector. You know? And I just want you to see it's an outer product. All right, cool. And maybe my yelling this semester, I've never yelled this much. Maybe it's a test. I want to see if it maybe gets more of you to absorb the notation faster. All right. So now that I've been yelling, what's going to happen if I take pi through? Well, let's keep this together, because that's p minus s cross nu is that matrix has non-negative entries. All right? But what's pi times s times nu? Well, that's a row vector, that's a column vector, and that's a row vector. So, yeah, all right. Yeah, I mean, no, no. A matrix times a row vector is a row vector. Yeah, but what row vector is it? What happens when you make it to multiply a row vector times a column vector? You get a dot product, exactly. So it's some delta times nu. And delta is just equal to, I'm going to write pi of s, even though it'll blow your mind. It's just a dot, again, it's pi s. It's just equal to the dot product. You know, row vector times column vector is a dot product. You know, and pi of s looks weird, I know, but I just mean the dot product. All right. Now, the fact that delta is pi of s, I don't care about that. I'm just going to take it as a number. All right. So I get that pi times p minus s cross nu plus some delta times nu equals pi. And you all can imagine what I'm going to do now is I'm going to take this to the, move things around. I saw so many nods, I'm going to write it down. I'm going to take this to the left-hand side. And flip things around, So what have I done? I've taken this, put it, move things around a little bit, re-scrambled. So I've got a pi here, yep, a pi there. I've got a minus pi times p minus s cross nu. That's because I moved this to the right-hand side. I've got the delta nu, so I just flip things around because it's the right order for me. All right? So I invert, I'm done. So everybody write down what mu is. All right. So I'm going to multiply by the inverse on the right-hand side. Oops. Right? And let's give that a name. I'm going to regret this, but right now I'll just call it Z. Z is actually usually used for something else. So this is just notation. I'm going to call that Z. It's a big matrix. And come on, what is Z, everybody? What's the inverse of a matrix like that? Let's just, no, it's this inverse. We're like I minus something inverse.
It's B minus this.
No. So remember, this is like my p tilde. You know, if I had chosen S to be a function with all ones, and if I knew is this pi, this was a power series. It's still a power series. Now, and guess what? If I scale an eigenvector, I get an eigenvector, right? The delta is irrelevant. You know, I've solved the left eigenvector problem. You know, and if you accept this has non-negative entries. Right, and nu has non-negative entries. So not only have we solved the left eigenvector equation, but unlike MATLAB, we have a non-negative solution. You know. And if you look at my definition of x star, in fact, this has to be strictly positive on x star. Pretty cool. So it sounds like I'm just advocating your solution, right? But I'm not. I'm just going to use the slash command in MATLAB. I don't have to invert this matrix either. I just have to slash in MATLAB, and I've got the answer. So it's insanely, you know, efficient. It's, you know, it's, you know. And so, yeah, I mean, I've solved the eigenvector equation. If you want pi, you renormalize. You know, if anytime you get a solution to the left eigenvector problem, you just renormalize it so pi sums to 1. All right. So where have I cheated? There's one place I've cheated. Well, I didn't cheat with the S and U because I gave you an example. So for a countable state space Markov chain, we'll forget finite. We don't need that. I can always do this. Yep.
Delta's a function of pi?
Nah. I think it's that basically, I mean, it's a good point, is that I went backwards and then I went forwards in a way. I said, suppose I could solve it, and then I said, go like this, I'd get this equation, and then I'd invert, and I'd get this equation. And I stand by my claim that this is going to be true, you know? So you're right, delta depends on pi, but I can ignore it in the end. I can just say mu equals this, and then renormalize, done. So I didn't cheat there. What's that?
Is that inverted?
Yeah, that's why I cheated. So what is the Perron-Frobenius genius? Genius. God damn, I didn't get enough sleep. The Perron-Frobenius genius is to prove this is bounded. And what they do is they prove that, in fact, if you take nu times the sum n equals 0 to n, of this thing. All right, so that's a matrix. You all agree with that? I hit on the left with the row vector nu, and I hit on the right with the column vector s. You prove that's less equal to 1 for all n. All right, and the proof is induction. It's really trivial. You know, for capital N equals 0, you could show that by the minorization condition it's true. And then it just turns out to be trivial. It's algebra. I almost started thinking I was going to give the proof, but it's just induction. It's nothing. And once you know it's true for capital N, you add 1, and you see everything cancels out. It's really fun. So if this is true for all n, then with the s and u in there, it's I can let n go to infinity, and I still get less than 1. All right? And then eventually you find this is finite on this X star set. Right? So that's really cool. That's the secret sauce. You know, all these steps would be meaningless if I couldn't show something like that. So this Z actually does exist on X star. So from this is a little more work. Oh yeah, and this is true always. Even for the countable state space case, and even unstable. This is what's really crazy, is that you can prove this bound by induction for a Markov chain that's completely transient on a countable state space. Like that Q problem, the MM1Q. Imagine the arrival rate's much bigger than the service rate. So the process just shoots to infinity, you know, maybe deterministically, just boom, and blows up. You can still show that this thing is finite valued, which means that this thing is well-defined and beautiful. What do you think happens then? Think it over. I don't expect an answer right away, but let this sink in. Yeah. All right, but isn't that cool? All right, so never, ever use anything but this to compute an invariant measure, as far as I know. I don't know of any more efficient way to go through and compute an invariant probability mass function for Markov chain. Is it clear? I mean, you're thirsty for algorithms. There's an algorithm. And you won't find this in many places. That's what's weird. I don't know why that's not in every textbook. You know, it's really strange. Yeah. You know, I've seen it. So far I've been saying it's a finite state space, finite state space, finite state space. But go back. Does that require a finite state space? I mean, no. Nowhere here do I need a finite state space. So countable, it's trivial. I would have to change the notation a little bit if I went to general state spaces, because this wouldn't be X prime anymore, it would be A. I'd have to look at sets rather than points. Yeah. But what the beautiful fact is that this monster here is always finite, even for Markov chain that's not stable in any sense. So pi needn't exist for this to exist. Yeah. Okay.
Is that a bad thing that it exists when it?
No, well, it's a good thing because it gives us a beautiful machine. So okay, so we've got our methods. We can do that. We can do that, but we'll always do this in reality. And so I'll explain why it's valuable now. Okay. But any questions?
Well, in MATLAB, we can get all eigenvectors with I. But
It's computational complexity. So if maybe you have a Markov chain with 10,000 states. You know, it's like, I don't know, 10,000. Solving this with 10,000 states. What do you think? I don't know. Would it be a second? And I wonder how long this would take. I don't know. I'll bet a lot longer. Yeah. Yeah. And also you have to sift through it. You got to find that positive guy. Yeah. And these things can be really numerically unstable. So, you can have problems where there's a lot of eigenvalues near near 1 and stuff. And, yeah. So this is,
I just kind of only see this like how you can get like, I see how you can get like a eigenvector, but I don't
no, this is we're only getting one. We're only getting one.
That's what I'm saying.
This does not work. Oh no. If you ask me to find the second eigenvector, Cohen-Frobenius does not help you. The key in all this was the fact that this thing, I know this exists because it's the sum of positive terms. So at first sight it could be infinity, but then you have this beautiful inductive argument to show it's actually less than, and this is actually less than 1. So to get the other eigenvectors, you're stuck. There's no theory. You have to use standard tricks. It's only the Cohen-Frobenius theory is a theory of positive operators. It's not even transition matrices. I mean, really, you can go through this whole thing with P not even being probabilistic.
So it only finds the one eigenvalue on the rim.
At 1.
Yeah.
No, the eigenvalue at 1. At 1. Yeah. Right. We started with this. We started with this. The eigenvalue 1. Well, just 1, not the unit circle. 1, 1, 1. Right?
Well, if it's always at 1, we know.
It's not. I'm not. I didn't assume aperiodicity. I didn't assume aperiodicity. So
Magnitude 1.
no, it could be periodic. No, it's only that. We only can solve that. I just don't want to, look, I don't want to confuse things by saying there's something else funky going on. To solve that equation, I can use Cohen-Frobenius theory, not anything else.
I'm trying to get it crystal clear.
Right there, it's crystal clear. There's no lambda. Right? I'm saying pi p equals pi, not lambda pi. That's all. Anything else will make it less clear. There's no lambda there. The lambda's 1. All right? That's what I'm doing. I'm trying to keep it clear. There's nothing clearer. There's nothing clearer than that equation. That's the goal. There's nothing more crisp than that. Okay? Okay, so let's think about this. What happens in the countable state space case? Well, I've told you this is completely general. This is still true, and therefore this thing is still finite valued on this reachable set. I'm still about the unit chain case. And so mu exists. And if I look at what I call mu of S, so right here, this is true for every n. I can let n go to infinity, and I get that mu zs is less than or equal to 1. Basically just let n go to infinity, and the inequality is preserved. And so that's still true. What goes wrong is that if you try to invert the steps, you don't get equality anymore. In general. Okay, so when I hit mu by p, I get a vector whose components are less than mu. Right? So mu is a row vector. When I hit mu by p, I get another row vector, and the components here are less than that. All right? Now, one way to get equality would be is if it's finite. So if it's finite, then what am I going to do? I mean, so this you can show, you know, again, you can show it by induction if you like. It's basically hitting this on the left by p and using this bound. Okay, it's just like it's a one-liner. It really is. I just feel like I feel like I shouldn't do everything. We have bigger fish to fry, but it's very, very simple to prove. You always get subinvariance. What happens if mu is finite? What would you do to show that you can't have a strict inequality there? Right eigenvectors. We still have right eigenvectors. What's the right eigenvector for p? Remember, there's an eigenvalue at 1. What's the right eigenvector? No, right. No, left was this guy. So that's the left. What? All ones. So we always have this. So luckily we've always got a right eigenvector, so we're safe there. So what happens is if it's finite, I can hit both sides by 1. And I'm not getting infinities less than infinity. We knew that. And so what you get is that you get that mu p1 is less than or equal to mu 1, if you like. So here I've broken my convention. I mean, no, I'm looking at dot product. Mu is a row vector, 1 is a vector of 1s. I know it's infinite dimensional, don't worry about that. That's a dot product. And so basically I have the string of inequalities, and of course the tails are the same, right? So this inequality can't be strict, or we get a strict inequality here. You know? So we have to have strict equality here whenever mu is positive. Yeah.
I'm not following anyone from then to the next one.
Where?
You know, when you said like right eigenvalue,
Oh.
I'm not following.
P1 equals 1. No. So what I'm doing is this is a row vector, that's a row vector. I'm hitting both. A row vector can be hit by a column vector. I'm choosing a vector of all 1s. And because 1 is positive, it preserves inequalities. So basically, I'm summing both sides of the inequality. You know, I'm writing this complicated way because I want to use the fact that p times a vector of 1s is exactly equal to the same vector. I want to use the right eigenvector equation. So from here, so this implies this is just from summing both sides of the equation. And again, this equals this from the eigenvector equation there, and this is equal to this by definition of dot products. And again, so if there was a strict inequality for one x, for which mu of x is positive, we get a contradiction. We get that the sum was less than the sum. We get something crazy. So that implies that mu p of x equals mu of x. And that's really enough. That's all we need. You know? Because it's positive exactly on this set x star, and that's where we live. I mean, we don't care about the rest of the state space. Okay, so if it were finite, then I'd get invariance. That's what I'm saying. Okay. So that's just a minor thing. So mainly, the most important thing is to say that nowhere here did I use a finite state space. So let's spend the rest of the lecture going back to our Lyapunov functions and showing how quickly we can validate that, just like that. I mean, I think it's 2 lines to go back to our Lyapunov functions, and just using this representation of mu, we can just instantly you know, sort of get a stability theory for these Markov chains. Oh yeah, damn. I think I've left something out. Ah. No.
It's kind of a lot to digest.
Yeah, sure.
Like, so the inequality right there, that was, you showed that was a contradiction. And
No, I didn't say it's a contradiction. I said,
and then so,
no, I didn't say it's a contradiction.
okay.
I said, what if it was strict,
We're
right?
straight.
What if this inequality was strict? What if what was less than? What it was, this was a half and that was 3/4, strict, right? You know, so then I sum both sides, right? And one of those terms is really bigger than the other, you know? So the sum would have to be bigger too, right? If one of those terms was strictly bigger than this, then the sum, I get a strict inequality here. But then I'd have this dot product is strictly less than itself. And that's a contradiction. And so that's where we have to have equality. Yeah? They must be equal. Now, if this were not finite, I would just get infinity is less equal to infinity, which damn straight it is. You know, that's the thing. So once you have finiteness, then you have equality. So then the trick is to have a criterion for it to be finite. And that only matters for a countable state space, but it is, you know, I mean, that's probably not my biggest objective, is to talk about countable state spaces versus finite. It's just that I want to get inside of these Lyapunov functions and how to get bounds. Okay? And these Lyapunov functions, any of the control people out there, they are value functions in control problems. I mean, that's what they are. We're talking about approximate value functions. Right? Anything else? All right. So let's go to the basics, the most basic one. Or maybe not. Yeah, let's go to the simplest one. But I realize that there's one thing I forgot to say here, I think. Yeah, bummer. So there's a few gaps in here. I'm not doing everything. I just want to give you the big picture. I forgot to say this. You can actually say something stronger. If you take Z times S, again, Z is this giant matrix, S is thought of as a column vector, it's matrix vector multiplication. You can show that this function of X is less than equal to 1 for all X. So that's even a stronger condition than I said. I forgot to say that. So that's pretty remarkable too. I mean, no stability needed. Again, induction. It's just basically take the finite sum and prove it's less than 1 for every n.
You mean in norm it's less than 1?
Nah. No, just what I wrote. Take a look.
HX.
H is a function. No. It's I'm looking. Oh boy. So remember. So this is a thing that a lot of people have trouble. When I talk about a function, I represent it as a column vector. When I talk about a probability mass function, I think of it as a row vector. So I'm just taking a correspondence between functions and vectors. All right? And so h of x is a number. How do I do this? It's really easy when we're talking about just a finite state space. You know, so remember, if x is equal to just 1, 2, 3, 10, right? And then I take a function h maps x to r, right? H is defined by its values at 1, 2, 3, 4, 5. You know, I write h as a function, but when I write pH, you know, I can think of it as a vector. And I completely sympathize. Everyone gets confused about this. I talk about functions, vectors, functions, vectors, functions, vectors. Why do I do that? That's why. You know? That's why. It's a function. H is a function. H maps the state space to real numbers. It's always a function. But when I hit a function by p to take a conditional expectation, because that's, I'm not going to write it down again, that's a conditional mean. It's when you see that it's disperforming matrix vector multiplication, shit, why not identify vectors and functions? You know? And the ith entry, the jth entry of that vector is h of j. Right? So x here looks abstract. Let's say it's an integer. X equals 1, 2, 3, 4, 5. X equals 5, that's the fifth entry of h. Viewed as a vector.
You just overloaded H.
Well, no, I'm evaluating. Look, h of I, j. I'm evaluating the entry. Right?
It's just overloaded.
Overload. No, it's just it's the entry. So h corresponds to a vector, which is h of 1, ... h of 10. And I'm just going back and forth from the vector representation to the function, vector, function, vector, function. And it always confuses students. It always does. So half of you are confused. You know, it's always a barrier when I teach this stuff. Okay? You're not alone. A lot of people are confused about this. All right? So that's a vector in R10. That's a function in R. I'm just equating them. Yeah, and so ZS is like matrix vector multiplication in the same way that's matrix vector multiplication. You know, that H, yeah, let's say countable state space. Can we do this? Nah. We get 10. Suppose it's the positive entries. That H there, H equals ZS. I mean, exactly in the same way. All right? Cool. All right. So, no, it's good. I want to be slowed down. I mean, I know this is a minefield in terms of notation. In terms of concepts, it's so trivial. It's really trivial. Yeah, you know that. All right, so let's look at something. I need this. I kind of wish I had proved this, but I won't. I'll send you a reference. There's something called Foster's criterion. So Foster in Cambridge and a bunch of Russians in Moscow at the same time were developing Lyapunov theory. Foster got the credit because of the Cold War. I mean, and if I'd done my homework, I would have given you the Russian, geniuses who were working in Moscow at the same time. But he looked at a countable state space, and he had this. He shouldn't think this way. This weird way of writing it, he wouldn't even recognize. But what is it? So that's the inequality we're going to look at. All these are all quote unquote vectors. They're functions, and this is pointwise inequalities like we had before. So what is S? It's a small function. I mean, that's, oh yeah, I forgot to say, those are called small functions. There we go. You know, so basically I'm exactly the settings before when I was doing all that nonsense over there. And Foster's criterion is saying this is a conditional expectation like we talked about before. It's saying that the conditional expectation of v of x t plus 1 given ft, given the history, well, no, forget that. This conditional expectation is equal to this. That equals that by the Markov property, right? And the thing that I'm asking you to memorize for the exam, the only thing outside of this, you know, the instructions, was to remember this is PV, evaluated xt. That's the definition of PV. The definition. When I write PV, I just mean the conditional mean, all right? Which is the same as that. And then I've got that's less than equal to this. And I could put in the plus, well, I'll put it in. But this little term here is going to be 0 outside of a bounded set in applications.